Right. Let's take a look at the acid-base properties of these amino acids, and it's a very important concept. So one reason that it's important is if we think about what our solvent is, again, we're talking about the human body. Uh, it's water, and organic compounds generally aren't soluble in water. Obviously, our amino acids are soluble in water. Otherwise, life really wouldn't exist. So let's go ahead and take a look at that. Again, we've got our amino acid, got some kind of R group. We've got our carboxylic acid, and then our amine. And there's the only naturally occurring ones are with the wedge, but I'm going to draw them with lines just because it's easier. So we can see that we have two functional groups here, right? We've got the amine and we've got the carboxylic acid. So remember that when we're talking about amines and their pKa values, we're actually talking about the pKa of the conjugate acid. So what we're talking about is this NH3 becoming an NH2 and then releasing an H+. And this pKa value usually occurs between 9 and 10. So slightly more acidic than water, but not any crazy amount. And then we have our carboxylic acid, which of course can act as an acid, so it can be turned into this O-, and then it releases an H+. And so the pKa here is actually about 2 to 3. And so the first thing that we notice is that the pKa value of the carboxylic acid is significantly lower, remember it's a logarithmic scale, than the protonated amine. So our carboxylic acids are actually more acidic than protonated amines, which might not be what you thought of at first, right? Generally, when you see this positive charge, that you have a more acidic component, but not in this case, right? This negative charge that does form is resonance stabilized between two very electronegative atoms, oxygen. So, it might not be how you thought of it at first. And then finally, let's take a look at the relationship between the pH, which is a measure of how much H+ is in our solution, and then and the pKa, which is a measure of our acidity. So if your pH is equal to pKa, to your pKa of your compound, what does that mean? It means that about half of the molecules are protonated, and then of course the other half are deprotonated. So for example, if your pH is less than your pKa, right? If your pKa is 5 and your pH is 1, your compound is going to be protonated. If your pH is greater than your pKa, and remember a high pH means more basic conditions, that means that your compounds are going to be deprotonated. And remember that protonated means that we add an H+, so generally protonated compounds are more positively charged, whereas deprotonated compounds, right, we're taking away an H+, so they're generally more negatively charged. So let's just take a look at our generic amino acids and take a look at what they look like. So we're going to have low pH over here. Remember, low pH is an acidic condition, so we have a lot of H+. We're going to put approximately neutral pH right here in the middle. And then we're going to do high pH over here, which remember that means very low H+ or a large amount of OH- since we're talking about water. And so we have a basic solution overall. So when we're acidic over here at low pH, everything is going to be protonated, which means that your amine is going to now be an NH3+, right? That's the protonated version of the amine. And then your carboxylic acid is just going to be the OH, just the neutral compound, because that's what a protonated carboxylic acid looks like. Again, a lot of people are tricky, right? They don't like the fact that this amine is protonated. Too bad it is. At more intermediate pHs, now we're going to remove one of these H+, right? And remember that the carboxylic acid is actually more acidic than the amine. And so what we deprotonate here is actually our carboxylic acid. So that becomes an O minus, and this stays as an NH3 plus. Again, a lot of people don't like that. You think you're going to deprotonate that positively charged atom first, and that is logical, but that's just not the way it works, right? And then finally, in high pH or basic conditions, we're going to deprotonate both of them. So this is going to become an O minus, and this is going to become a neutral NH2. It never becomes an NH minus. That is way too strong of a base to exist in the human body. Cool. This one right here with approximately the neutral pH is what happens in our body, right? So the physiological pH is equal to approximately 7.4. So you can see that's approximately neutral, right? A neutral pH is 7.4. That's pretty close. So this one in the center is the form found in the body. Generally, of course, there are always exceptions. And then what we notice about this molecule, it has both a positive and negative charge. So it's net charge. If you add up all the charges, it's neutral, but it does have charges. And so this is what's known as a Zwitter ion. And a Zwitter ion is overall neutral, but it has charges. Right? It's got positive and negative charges, but if you add them all up, they cancel out. So acid-base chemistry, very important in biochemistry, very important in the human body. Except when you're talking about drinking basic water or high pH water, that's just marketing mumbo jumbo. What's funny is, let's take a look just real quick at the way all of these are drawn, right? They're all drawn as neutral, with the amine being deprotonated and the carboxylic acid being protonated. If we look at our three structures, that structure is actually the only option that never exists, right? So it's kind of funny. We always draw them as overall neutral, but this is actually the only form that doesn't exist. Where we have an overall net neutral charge and we have no protonation, right? And that's the reason that it doesn't exist like this, is because carboxylic acids are more acidic than protonated amines, right? So, if this compound really did exist, this amine would just grab this H off of this carboxylic acid. So anyways, that's funny. pH, very important. pKa, very important when it comes to biochemistry and amino acids.